All right, I'm gonna give this a second try because I got through about 15 minutes of the last video and had to restart. So hopefully that doesn't happen this time. All right. So this is the intro to exponential functions. All you really have to do is watch the video, take notes on your exact same handout and see if this stuff makes sense. And we'll do a problem kind of like it tomorrow. I will be checking your notes though, so make sure you're actually taking notes. Um, so in this one, the intro problem here, and we're only doing one problem, is about a university tuition in 1980 was $4,000, and then every year for the next 8 years it goes up by 6%. So the questions are about, well, how does the tuition change from year to year? Well, in 1980, the tuition was $4,000. That's given. Okay, in 1981, that's 1 year later, it went up 6%. So the way that you're going to want to train yourself to think about that is that you want to increase by 6% from the original $4,000. So what you really want is 106% of 4,000. And the reason for that is that you've got 100% of the original amount. So that's the 4,000. And then you're going to increase by 6% more. And if you remember 106%, in order to get 106% of something, you multiply by 1.06. So the value here is going to be 4,000 times 1.06. And then I got a calculator here somewhere. Let's see. Oh, come on, turn on. There we go. 4,000 times 1.06, enter, 4240. So that's how much tuition cost in 1981. So it went up a couple $100, $240. Okay, so in 1982, what we want is 106% of the previous year's value. So I could do 4240 times 1.06, but the way that I want you to, so look over here, when we get to 1988, I don't want to have to figure out what 1987 is and then multiply that by 1.06. So instead, you want to train yourself to think about this value here. I want 106% of the previous year because it went up by another 6%. Well, I could do this guy times 1.06, or I could do 4,000, this whole value here, times another 1.06. So let me write that out. So we got 4,000 times 1.06. And then, so that's the previous year. And then I want to multiply that by another 1.06. So this part right here is the previous year. And then this is the new 106%. So I'm taking 106% of the previous year. Okay, well, another way of writing that is 4,000 times 1.06, 6 squared, because there's two of them. And then if you plug that into your calculator, 4,000 times 1.06 squared equals 4494.4. 0.40, because it's dollars and cents. Okay. Well, I'll just toss in right here. What about 1983? So then you'd want 106% of 1982. So you could take 106% to multiply the 4494.4 by 1.06, or you could take this guy and multiply it by another 1.06. So in that case, that would turn into 4,000 times 1.06 cubed, because you multiply by one more 1.06. So you get some answer for that. I'm not going to worry about what that value is. Okay, let's look at 1988. Well, that's going to be 8 years later. 8 years after 1980, the initial year. So in that one, I'm going to take 4,000 and multiply it by 1.06 to get 1981, and then square it to get 1982, cube it to get 1983. I'll raise it to the 8th to get 1988. And if you do that, let's see what that equals. So I'm just going to call up that one, and then go back and change that to an 8. And we get 6375.39. I'm rounding to the nearest cent. Okay, 2015, let's see, 2015 minus 1980, that's going to be, whoops, 1980. Why won't that 8 work? 80. That's going to be 35 years later. So 35 years after 1980. So in this case, we're going to do 4,000 times 1.06 to the 35th. So let's see what that equals. 4,000 times 1.06 to the 35th. All right, now we're up to $30,000. $30,744.35. Okay, so it's jumped up now. All right. T years after 1980, well, if you think about it, this is t equals 0, this is t equals 1, t equals 2, this one is t equals 8, t equals 35. And notice that the year always ends up right here. In fact, this one, you could write 1.06 to the 0, which is 1. So that's just still 4,000. So really this formula even holds when the year is 0. So t years after 1980, we can say that the cost, I'm writing a function now, is going to be 4,000 times 1.06 to the t. All right. So let's graph a model. Okay. So here's what I'm going to do. I'm going to make a little table of values here. Time, the years, and the cost. And we figured out some of these things when it was 1980, so 0 years after 1980. The cost was 4,000. And then, let's see, when t was 1, we had 42.80. And when t was 2, we had 44.94. When t was 8, we had 63.75. Oh, that's 0.4. And this is 0.39. When t was 35, we had 30,744.35. I'll throw in one more. Let's do like 25 also. So if we do 25, we've got 4,000 times 1.06 to the 25, and that ends up being $17,167.48. Okay, so that's enough to create a table, or a chart here, a graph. So let's make some X and Y axes, although really the X axis is time in years since 1980. And the Y axis is really the cost in dollars. And let's see, the T values that we looked at went from 0 up to 35. So here's 0. We'll make this, we'll go by tens here. So 10, 20, 30, 40. And then the costs went from 4,000 all the way up to 30,000. So let's do 5, 10, 15, 20, 25, 30, 35. So 5,000, 10,000, and then I'll skip up to 20,000, and then 30,000 up here. Okay, so let's plot some of these points. 0, 4,000 would be right about here, let's say. And then 1, 4280 is really, really close to it, like there. 2, 4494 is also pretty close to that, so maybe like, there. 8, 6375, that's a little bit higher, maybe like here. 35, 30,000 is way up here. Oh, 35. So like around here somewhere. 25, 17,000 would be like around here. If you plotted 20, I'll just tell you now, if you put 20 down, you get 12,828.54. So if we plot 20 around 12,000, like around here, you can kind of tell this thing is not looking like a straight line. It doesn't do this, right? In fact, it looks more like it curves up as time goes on. Okay? And if you think about it, if you go backwards in time, and it was still increasing by 6% a year, you're never going to have tuition be negative. So it just means that the tuition backwards in time was closer and closer to $0. So one thing I want you to note here, right, when you approach 0 way out there at the line y equals 0, remember that thing's called an asymptote. So an asymptote, so I'll write note here, or notice. Asymptote is y equals 0. Right, it gets really close to y equals 0 down there. This thing is not a parabola. It doesn't come back up. It doesn't make sense that it would go back up, backwards in time. It's not a line. So it's this new thing that we have called exponential. So this is called exponential growth. Okay? So I want to come back up here to this equation and define a few terms for exponential growth formulas. Okay, so this value right here, that's our initial value, right? That's the value that you started with, initial value. And notice here, that's also the y-intercept, right? The 1.06, since it's bigger than 1, when you multiply by it, stuff gets bigger. So this is called the growth factor. And then there's one other thing that's kind of built into the 1.06. The 6% is called the percent increase. Okay? All right. So let's go on. Oh, and this whole thing right here is called an exponential function. And the way that you can remember that, the idea is that the exponent is the variable now. So the variable's not like stuck in the middle. It's now the actual like x term or t term in this case is the power itself. Okay. Well, what if the pattern had been true before 1980? So let me rewrite the function that we had for the pattern, 4,000, 1.06 to the t. So the question is, what was it in 1970? Well, 1970 is 10 years before 1980. So what you can think of 1970 as is t equals negative 10 years, right? So I'm going to plug in negative 10 years earlier. 4,000 times 1.06 to the negative 10th. So let's see what that gives us. 4,000 times 1.06 to the negative 10th. 2233.58. Okay, and let's look at the graph. Well, negative 10 would be about here. That'd be 1970. And you can kind of see on the picture, yeah, it's around 2,000, 2,500, somewhere in that range. So that makes sense. And if you kept going back, it would just get closer and closer to 0. Okay. So let's see. Not that this ever actually occurs, but what would change in the model if the tuition decreased by 6% a year? So let me write the original. C of t was 4,000 times 1.06 to the t. That's a 6% increase. We want a 6% decrease. So let me do this. Actually, I'll erase this. So instead of wanting a 6% or wanting, let's say wanting 106% of the previous year, we'd want 94% instead, right? And where did the 94 come from? Well, that's the 100% is the original amount, and then we're subtracting the 6% because of the decrease. So then that would mean that our new function, would be C of t equals the initial amount, 4,000, times, and instead of 106%, we're doing 94%. That's 0.94, right, to the t. So let me write a couple things here. That 4,000, that's still called the initial value. The 0.94, well, that's less than 1. So every time you multiply by another 0.94, you're decreasing. So another term for that in math, when you decrease by 1%, it's called decay. So that's the decay factor. And the decrease is 6%, which you can get because you can think of it as 1 minus 0.06. It's the 100% minus the 6%. So that 6% is called the percent decrease. Now, each year the tuition is going to go down then if you're decreasing by 6%. So it doesn't make sense that the graph would do this, right? Instead, what happens is you get a graph that goes like this instead. So it gets lower and lower and lower. Let me draw a better version of that. So as the years go on, your graph will actually start out high and then get lower and lower and lower. And this point right here, that's your initial value of $4,000. And if you keep decreasing by 6%, you can never go negative. You just get closer and closer and closer to $0. So notice right here, it approaches the line y equals 0. So an asymptote is y equals 0. Okay? And then this thing, it's not exponential growth. Instead, this is called exponential decay. Okay, I want to do one other thing with you. So go on back up to this graph. I want to talk about the end behavior here. So what happens as t gets really, really big? So as we go to the right, as t gets bigger, then what happens to the cost? That also gets bigger. That shoots up to infinity as well, right? If you remember that idea. And you can get that by looking at the equation right here. If you plug in like 1 billion for t, you keep multiplying by 1.06. That's not a huge number, but if you multiply by it 1 billion times, this 4,000 gets bigger and bigger and bigger. So that makes sense that it should shoot off to infinity. If you come down here and you plug in infinity for t, or plug in like 1 billion, well, you keep multiplying by stuff that's between 0 and 1. So it keeps getting smaller and smaller and smaller, so eventually it turns into 0. So as x goes to t goes to infinity here, the cost goes to 0 instead. Okay. We could do it backwards too, right here, as t goes to negative infinity. So if you kept going backwards in time here, the cost would go to positive infinity, which doesn't make a ton of sense. Usually stuff doesn't decrease in value over time, it increases. So it doesn't make sense that if you went backwards in time, it would get more expensive, but whatever. Okay. All right, I hope that makes some sense. Tomorrow we'll do number 2 in class and kind of build off these ideas. Okay. I gotta figure out how to stop this video.